Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 17, 2025, about 6 days ago. In this paper, the authors formulate and prove fundamental architecture-agnostic limits on how large language models scale, arguing that problems like hallucination, limited usable context, degraded reasoning, brittle retrieval, and multimodal misalignment are not just bugs, but in many cases are mathematically inevitable consequences of computation, information, and learning theory. The paper is titled, On the Fundamental Limits of LLMs at Scale. And, as we will see later, the implications for how we train and trust large language models are quite significant. Alright, the introduction set up the big question about whether scaling alone can fix language model failures, and Figure 1 maps out the 5 fronts where that hope breaks down. The figure shows long context limits, brittle reasoning, hallucination, fragile retrieval, and multimodality issues as connected pipelines. Each row traces how realistic inputs move through the system and where failures arise, such as context overflow, prompt contradictions, or noisy retrieval. The arrows highlight that these fronts interact, so fixing one in isolation rarely removes the deeper limitations. So, while Figure 1 framed the broad fronts where scaling hits limits, Figure 2 digs into why hallucinations in large language models persist. The top half groups fundamental causes, including diagonalization, uncomputability, and statistical limits that guarantee some questions always trigger errors. The right side adds data failures such as noise, long-tail facts, and temporal decay. The bottom panels show how benchmarks punish honest uncertainty, then how temperature and diversity create a creativity versus factuality trade-off. Together, these blocks argue that hallucination risk is baked into both theory and practice, not just into bad training runs. Well, Figure 3 turns those theoretical data problems into concrete patterns. The left panel shows accuracy staying above 95% for popular entities, then plunging below 40% once entity popularity drops under about 100 page views per day, so rare names almost invite hallucinations. The right panel shows factual validity over time since training, with fast-moving domains like news sliding under 50% within 6 months, while static facts barely change. Alright, while Figure 3 showed how rare facts drive hallucinations, Figure 4 explains why long contexts are undertrained in the first place. Figure 4 shows position frequency during training, and both curves drop steeply as token position increases, so late tokens almost never appear. The blue 4K curve decays more slowly than the red 2K curve, yet both leave the far right of the window scarcely trained. This skew means models mainly practice using nearby context, not truly long-range dependencies. Okay, while Figure 4 highlighted that late positions barely get trained, Figure 5 lays out the 3 concrete bottlenecks on long context reasoning. Left block shows skewed training distribution, so models learn a short effective window, even if the nominal window is huge. The middle block shows positional encodings that lose overlap as distance grows, which makes far apart tokens look unrelated. The right block shows attention computation that must fight distractors and quadratic cost, so practical sequence lengths stay limited. Annotations. So, while Figure 5 described the 3 theoretical bottlenecks, Table 1 turns them into a practical checklist for long context design. Table 1 lists specific issues like positional undertraining, positional encoding attenuation, and softmax crowding, then describes how each one harms the use of long inputs. The next column outlines targeted fixes, from data curricula and index remapping to modified positional encodings and sparse attention. The final column points to key reference papers, so the table effectively serves as a playbook for partially mitigating long-range failures rather than eliminating them. So while Table 1 acted as a checklist for long context design, Figure 7 presents 4 concrete reasoning strategies that wrap around language models. The left block shows chain of verification, where the model first answers, then generates checks, runs tools, and revises its final response. The second block depicts program-aided language, which converts questions into code that external engines execute. The third highlights neurosymbolic integration that couples neural models with explicit rules for multi-step logic. The right block illustrates multimodal grounding, where image and language inputs jointly guide a more reliable response. So the big message is that some weaknesses of large language models, like hallucinations and short effective context, are not just engineering bugs, but flow from deep limits of computation and information. At the same time, the work points to partial fixes like better retrieval, curricula, and hybrid neurosymbolic systems, so progress remains possible but bounded. Thanks for joining this episode of the AI Research Roundup. I'm Alex. Thanks for listening.